In this lecture, we're going to look at continuous dynamic optimization phase diagrams. This is the second lecture on this topic, and we're going to look at examples for the most part. So an illustration of a phase diagram is one where we have x dot equal x times 4 minus x minus y, and y dot equals y s 6 minus y minus 3x. So in some ways, this is a nonlinear differential equation, or both of them are differential equations that are nonlinear. We find equilibria by setting x dot equal to y dot equal to 0, and we find that there are four equilibrium points, 0, 0, 0, 6, 4, 0, and 1, 3. So we're going to test local stability in step 2 of each of the equilibria, either using an eigenvalue method or exploration. It turns out that 0, 0 and 1, 3 are unstable, and we're going to show that, and 0, 6 and 4, 0 are stable asymptotically. And we draw the isoclines, which we discussed in the previous lecture, and this is where x dot equals y dot equals 0, and directional vectors all point in the same direction. So here are the four isoclines. The first one is y dot, this red line. The second one is y dot equals 0, is the horizontal axis. The third one is x dot equals 0, is this blue line. And the final one is x dot equals 0, the vertical line. And we identify these equilibrium points, 0, 0, 1, 3, which is this one here, 1, 3, 4, 0, and 0, 6. So those are our equilibrium points. So in step 4, for each region in the graph, we find x and y directions. X does not change along the x isoclines, and y does not change along the y isoclines. So here are our directional arrows. You'll notice here it's kind of tight between these two, and here as well. And of course we have to take into account the fact that both axes, the x dot equals 0 axis or y axis, and the y dot equals 0 or x-axes in this case. So we have to look at those individual points. So let's first look at the stability of point 4, 0. So 4, 0 is here, and we see from these directional arrows and these separate traces that we've built, the two of them here, they indicate that we're moving towards 4, 0. All the arrows are pointed toward that point 4, 0, so we have a very stable point at 4, 0. The stability at point 1, 3, 1, 3 is here. Okay, and we again construct these separate traces along here, these two here. We don't show the other one. Well, we do. It's this black line that's got arrowheads on it. And we notice that if you look at these directional vectors here and here, that the black line indicates that if you're on one of these, on a separatrix, on this one in particular, you're moving away from the equilibrium in this direction and in this direction. You're moving towards on this separatrix. Now it turns out that if you're off of this particular separatrix, then your movement's going to be in this direction. So what kind of a solution do we get? Here we get a saddle point solution. Unless you're somewhere on these points, you're going to go away from the equilibrium point. So a saddle point equilibrium. Now, we could look at the other ones as well, but I'll leave that to you to look at. Let's consider a fisheries or a wildlife model. The logistics growth function for a fish or wildlife population is given by this particular function where dx dt, or x dot, is equal to some intrinsic growth rate given by gamma times x, 1 minus x over k, where k is the carrying capacity of the ecosystem. The harvest function in the traditional Gordon Schaefer model is the Schaefer production function, where harvest at any time t is equal to a catchability coefficient q times effort at time t and the stock of fish or wildlife that's available at time t. So then we can set dx dt equal to 0 to find the steady state solution. And when we do that, we end up with that x is equal to k, 1 minus q times effort. So the catchability coefficient times effort divided by this intrinsic growth rate. And the sustainable harvest then ends up being y equals QEX, or y is QE times k, 1 minus QE over gamma. This has the same shape as the logistics function as we show in this next diagram. Here's the yield effort curve, and we multiply it by a particular price, and then we get the total revenue curve. So this becomes the total revenue curve as soon as we multiply this by a fixed price. And we do that here, and we find the bionomic equilibrium, which is E infinity, where basically we've got total cost is equal to total revenue. Notice that total cost is equal to the per unit cost of effort, and this is effort plotted on the graph on the horizontal axes there. So this becomes our open access effort, because this is where total cost is equal to total revenue. The maximum sustainable yield effort is the one that gives you the maximum sustainable yield, and you can see that if you increase effort beyond that, total revenue declines. If you reduce effort, it also declines, so it also is where you maximize total revenue, which is rarely what economists are interested in, because we're interested in maximizing the difference between total revenue and total cost. So we do that here. We have a parallel line to the total cost function here, and we end up with E sub pi as being the effort that would be in a non-open access situation. In fact, that would be where somehow there's a control on the amount of harvest so that profit is maximized. Now we can look at the dynamics of the situation, and we can see that if this is the stock of fish or wildlife on the horizontal axes, then we impose this logistics function on it, which is x dot equals 0, and then y dot is the harvest or growth. Here it's the harvest, and this function looks like this. And we get these different stages, 1, 2, 3, 4, and you'll notice that the direction is in this direction here. It's away from it here, this direction, and away from it again. So basically what we're going to see is that there's going to be a separatrix here, and that's exactly a saddle point equilibrium as it'll turn out. So y dot is the derivative of harvest with respect to time in a fishery not characterized by open access. All right, notice that this here is our K. This is K, our carrying capacity. And notice that it's a stable equilibrium point right here. And we always and this is one of the downfalls of the logistics production function, is that even if we have a stock that's just about 0, we're going to end up going to this X star or beyond to K. If the X star applies only if we apply effort to try and harvest this. And here you could see that you have a saddle point equilibrium with, we haven't drawn that, here's the separatrix that's in there. And it's the most common equilibrium when you have one control and one state variable. So if you're on this line here, you go to the stable equilibrium. If you're anywhere off it, you're going to go to, in this direction, to extinction. This will be extinction as well. And in these directions, you'll end up going to the carrying capacity of the resource. So with open access resource exploitation, you have the potential for extinction. Consider a simple example where the starting point determines whether or not extinction occurs. The phase diagrams are provided below, and E refers to effort and X to the stock of fish or wildlife species. So here we have effort function, the E dot, the change in effort per unit of time is unchanging at X infinity. And here we have X dot is equal to 0. And we see here that we have these directional arrows. And when we look at that, so if we start right here, we end up going through here to extinction. Then if we go to the other diagram, we can see that the black path leads to extinction as shown above, and the red path leads to a steady state solution, but we get a spiral to that steady state here. And notice again that this is your open access amount. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.